4, and then you go through and you distribute again. This is where things start getting a little ugly, okay? Because you distribute that through, you get this line, you change the signs, you add down, these cancel, and then the next one you'll get is this. So what do you multiply at 1 by to get that? Well, that. And you keep going, and it matches up exactly with what he had. Understand that? So going back to the student, you know, the professors, and this is the way classes turn into later, you're getting these notes, right, and you're writing them down frantically, and you're trying to, you know, just get what's on the board down on paper. These steps that they're showing you, or that they're not showing you, are not assumed to be done mentally, okay? But it's that you could do that if you needed to, if that makes any sense at all. So no one's going to expect that you could just look at that and be like, oh, sure, yeah, of course, that's 1 plus x squared over 4 plus. No. But to sit there and say, hey, how do you do that? That's impossible. Just shows that you have no exposure to this sort of thing. And so the professor, I can kind of understand his frustration with, I'm not going to sit here and spend the next 45 to 50 minutes teaching people how to do polynomial arithmetic, right, of infinite polynomials. That's not within the scope of this class. Yeah. I think, honestly, he didn't know if the guy was just messing with him, like, you know, like trying to sidetrack him or something. I don't know. Whatever. Okay, so what do y'all think? Think you can handle that?
Yeah.
So problems number 55 through 58. I signed that last class, didn't I?
Yes.
Those problems are all of this type. So please take a look at those. Pardon?
Real quick.
Yeah.
Now, negative 5x to the 4th
Uh-huh.
plus x4 to the 16.
Yes. Common denominator.
And you took it out, right? You took the x to the 4th out. And it's negative 5 over 192, and you get your common denominator.
Yes.
But you don't reduce it?
Negative 5 over 192 plus 1/16.
Yes.
And you do that, get a common denominator, put them together, and you'll get 7 over 192.
Oh. So it's 7 times 8 times 16. Okay, cool. I
You
was
good?
wondering how you got the 7. I was like, what?
You all right?
Yeah, I got it. Now,
Okay. All right.
Thanks. I was asking. I was just like, wait, how did you get it? This is the last. Definitely the last thing.
There we go.
Thanks, man.
So we are done, all right?
We made it.
You made it. But I'm just going to state a couple of things. You know, the course description for Calculus 2 has us going up through a pretty good chunk of Chapter 9. Now, the reason why we are not doing that is because we didn't have enough time, number one. But the reason why I can sleep at night is because I believe that Chapter 9 is something that you, when presented it, you would be able to absorb it pretty easily, okay, the Chapter 9 stuff. When you compare it to Chapter 8, when you compare it to techniques of integration, I mean, this is more in the lines of like arc length and surface area, where it's just a formula that you apply. It's kind of the same, sort of in the same ballpark to me. And anyone that would take me for a Cal 3 class, I would never assume that you could do all of this stuff in Chapter 9. So a lot of times it's presented later almost fresh, okay? So just want to say that. I think the furthest I've ever got in a Cal 2 class is I had like half a day or maybe one full day on Chapter 9, and for everything in Chapter 9. So one day is the most I've ever had, because I spend so much time in sequences and series and so much time back with integration techniques. So, all right, let's talk about the final. So let's look at this. I know it's not the type of review that you would like. You would like me to just hand you a bunch of problems and say, hey, do these. Yeah, good luck.
That's cold, man.
Good luck. What movie is that from? Good luck. Taken. I like that scene.
Oh yeah. It says all deep voice.
Good luck. Okay, find the volume of a solid of revolution. You're going to take, basically what's going to happen is I'm going to give you a function. You might have to figure out, where it starts and stops, and you're going to have to rotate this around an axis. It might be the x, might be the y. But you're going to try and find the volume. On the test that you did in class, all you had to do was set up the integral, and that was it. You were done, right? You're either going to use washers or shells for that. Once you set up the integral on the final, I'm going to ask that you take that integral all the way to the answer. And I'm giving you a hint here that once you set it up, which it'll look like pi integral, like what, like function squared or something like that, or you might have something like this, f minus g. There's depending on washers or shells, right? It just depends. But that answer right in here, this integrand, you're going to have to integrate it. And you're going to have to use a technique of integration. It might be, it's probably not going to be just a basic u sub, all right? It's going to be a technique of integration that requires a little bit that shows me that presented with this sort of issue later, you're not going to be like, well, I don't have no idea. That was a long time ago. All right? So integration by parts, trig sub, right? Something like that. Be prepared for that. Okay? All right. The rest of the test is pretty much chapter 8. Given a series, so if I write a series out, can you come up with with its sum? So if I tell you to find its sum, what can you tell me? For sure, the series is either
Infinite?
no, it's going to be infinite.
Convergent or divergent?
It's either geometric or telescopic. Those are the only types of series we could find sums for in this class. So if I do something like, I don't know, 2 minus a third, I'll make it 4/3. No, don't make it 4/3. Make it 2/3 plus 2/9 minus 2 27ths plus 2/81. If I ask you to add that up and I say find the sum, and I'm telling you find the sum, that means it adds up to be something. That means it's either geometric or telescopic. What would this be? This is 2 1/3 to the n, something like that, minus 1, n is 1 to infinity. Does that work? I'm missing something.
-1.
I need a negative in here, right? This needs to start
A positive.
as a positive. So can I put a negative in here like this? Because if I let n be 1, what happens? I get 0. This to the 0 is a positive number. That should do it. Understand? So this is what type of series? Geometric. R is -1/3. The absolute value of that is less than 1, so it converges. It converges to a over 1 minus r. And a is 2, and r is -1/3. So this is 2 over 1 plus a third. Got it? Finish it. That's the type of thing. You need to be able to look at this, come up with the formula. That's something you're going to have to be able to do. And then from the formula, manipulate it to the point that it looks like, right, it has to look like geometric, which is one of two things. Or your choice, all right? Next type, telescopic series. Those are series that when you start writing them out, things start canceling away. And there was some question from some of your classmates about where this is in the book. Like, where's the homework that you can look at to look at telescopic? And it was in 8.2, so it's page... Oh, shoot. I'm glad you did that. That reminds me. page 443, okay? Page 443, numbers 25 through 28. Y'all catch that? Those are telescopic.
We can still use that trig sheet you gave us, right? With all like the to help with trig sub.
You want that sheet?
I mean, I still have it. I'm just saying we can still use it. Right?
Yeah, I won't change that.
He gave us a sheet with all.
Y'all okay on telescopic, or do y'all want to see something in terms of... You sure? Okay, we have 20 minutes. I want you to utilize the time we have. Let me just show you one of these. For number 25, it's sum n equals 2 to infinity of 2 over n squared minus 1. Okay, so what you would do first is partial fraction decomposition. You have to take this and do partial fractions. That'll turn this into a sum that has two things. I think they wind up, one of them gets subtracted from the other, like this. And then when you start writing the terms out, you start to get the cancel. Do you remember me talking about this? Like the first guy here cancels with the second guy there, and you find the pattern? That's what this is about. On number 26, they give you some natural log of n over n plus 1. And you can't see that this is a telescopic series unless you use the property of logs first, which allows you to turn division into subtraction. Right? That's what that is. And then when you start writing out the terms, you get cancellation. Just remember on this, go back and review, okay? But just remember, I have to see S sub n. You have to write it down. You have to show me the cancellation. Then after you get all the cancellation, you take the limit as n goes to infinity of this. If you don't write S sub n down and do the steps that I told you have to do, then I'm going to take off for it. I was pretty clear when I said it too, so if you've forgotten, go back. Number 27 is another partial fractions. And number 28, you can see the cancellation. I'll let you mess with 28. Okay, next thing on here. Determine the convergence or divergence of a series. Also, I'm not telling you that you're going to have one of each of these problems. Okay, I'm not saying that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not saying there's 10 problems on the final with this, all right? There might be more. Okay, there won't be less, but there might be more, all right? Determine the convergence or divergence using series test. So for that bullet point there, what I want is just to give you a couple of series, make sure you're comfortable using the different tests. And you're free to bring that sheet, okay, and use that on the test. That's a gift. You're welcome. You're welcome. Paying you back for helping me out there. The series test paper you can use on the test, all right? That allows, but that means that, you know, what I give you, I'm not going to tell you use the integral test to show that this converges. I'm just going to let you figure it out. And we saw in class that some tests, you know, you can do one test, you can do a different test. It might take you 5 minutes, it might take you 30 minutes. So you're going to have to show that you can be efficient. Yeah, ratio. Yeah, don't swing at those. See, here's the thing with those problems. I'm going to want to see that you can do something other than ratio because I know I'm going to get you with ratio later. Keep that in mind. So if you throw ratio at it, most likely it's going to be a problem that I'm going to make that can't be done with ratio. Just to make sure you can do the other tests. The what? The nth term test? Oh, just make them all nth term tests. All of the limits go to like 1 and sweet. Yeah, but don't forget that also. I'd hate to see you spend 30 minutes on integral test and show it diverges, and at the very beginning you could have done nth term test, right? Okay. Yeah, exactly. All right, given a function, find its power series using a geometric series. That is specifically referring to 8.6, page 474,
That's what give us a function, right?
problems 15 through 20. The one that says given a function, find the power series and using geometric series, rewrite. That's 8.6, page 474, numbers 15 through 20. And I also put there, you may need to differentiate or integrate the power series. All right, the next one, find the Maclaurin series using table of derivatives. That's last class, where we put the n's over here, we put the derivatives, then we plugged in 0 into the derivatives. Maclaurin series, so you're going to plug in 0, and you find a pattern, and you write out the series. Create a formula. The next one is the same exact instructions, same exact type problem, but this time for a Taylor series, so now A is something else. That's right, A is not 0. And then estimate an integral using Maclaurin series. I need to show you one of those still, so I'll show that to you in a second. The last type, use a table on 484, which again I will provide you on the test, to find the first few terms of a Maclaurin series. You may need to multiply or divide the two series to do this. So that's exactly what I did today. And you have a couple of problems that you can practice from that homework assignment. All right? Any questions? All right, so let me give you that example that I planned on. All right, so here's what I'd like to do. I'd like to approximate the integral from 0 to 1 of sine of x cubed dx. And I will start motivating this idea. I only have 15 minutes left, and it won't take me 15 minutes. I'm just going to go to Wolfram Alpha again, our good friend here. And I'm going to type into it, integrate sine of what? X cubed? Whoa. Off a little. This keyboard's weird. The shift key is like really small. Sine of x cubed. So let's see what Wolfram Alpha says to that. Oh my goodness. Whoa. It's bringing in the gamma function and imaginary numbers and all sorts of crazy shit in there, right? Like, this is basically telling you no technique of integration you have is going to solve that problem, all right? There's no technique. And there are a lot of functions out there that can't be done. And this is where I have problems with you can't do that. But we can, right? We can approximate it. So what we're going to do is just write out this series. It's sine. We know how to expand sine into its Maclaurin series. It is what? X. Good. X. But here for us, what's x? X cubed, right? Minus, then it's supposed to be x cubed over 3 factorial. Okay, so it's x cubed over 3 factorial plus x cubed to the 5th over 5 factorial. You with me? Minus x cubed to the 7th over 7 factorial. And then how far do we want to go? Well, it's an approximation. So let's maybe just go like one more. And the thing is, we can go as close, right? That's the whole point. We can go as good as you need me to go, right? As good as you need me to go, I can go.
is this gonna be one that we're gonna find like a bit of, like using the table, or you?
Yes, you would use the table for this.
Okay.
Absolutely. Yep. And I'm going to evaluate that 0 to 1. Right? Oh, wait, hold on. I haven't taken the antiderivative. Oh, hold on. Hold on. Got to take the antiderivative first. Maybe we can't do it. Okay, so x to the third minus 1 over 3 factorial x to the ninth. Remember, we're multiplying powers, right? I'm not doing an antiderivative yet. I'm just cleaning it up. X to the 15th minus 1 over 7 factorial x to the 21st plus 1 over 9 factorial x to the 27th. Right? Dx. Now antiderivative. And all these are just numbers right in front, so they're just going to come along for the ride, and I just got to do power rule a bunch of times. May I erase the top? Don't need it? Okay. And what do we get? 1/4 x to the 4th minus 1/3, or 1 over 3 factorial, and then whatever constant comes down there with it, 10. I can put the 10 in front or behind, it doesn't matter. X to the 10th.
Could you put 2 times 3?
Yes.
1 times 2 times 3?
Yep. We're actually gonna evaluate this in a second, so we're gonna have to figure out what all these numbers are. All right, next one, plus, let's see, 1 over 5 factorial times 16, x to the 16th, minus 1 over 7 factorial times 22, x to the 22. One more. Plus 1 over 9 factorial times 28, x to the 28th. And I'm evaluating that 0 to 1. Aren't you happy I said 0 to 1?
Yes.
Yes.
We don't even need to worry about the second row.
Yeah, 0 in there is killing everything off, right? We got lucky with that. So 1 in there is actually nice also. So this is just 1/4 minus, now let's go ahead and do this. That's 6 times 10, that's 1/60th, plus, all right, 5 factorial, you need a calculator here. 5 factorial, 120 times 16, right? 1,920. Anyone else get that? Okay, minus, what's 7 factorial? Where's my factorial? Doesn't matter. 5040? 5,040? Times 22? Ooh. 1 over 110,880. These numbers are getting really small really fast, right? Which means that my answer is going to be pretty darn close pretty soon, right? It doesn't matter if I go out like the first, 1, 2, 3, 4, 5, right? The first 5 terms aren't going to be much different than the first 100 terms because they're so small at the end. I'll do one more. 1 over 10,160,640 plus, oh, that's it. This is finite. Now I'm going to get this, and I'm going to actually get this as a decimal. Okay, so I'm going to do 1/4 on my calculator. Minus 1 divided by 60 plus 1 divided by 1920 minus 1 divided by 1 plus 1 divided by 1. Did anybody else get something approximately equal to 0.2338? Yes? No?
Yeah.
Yes? Are you just being agreeable? Okay. I want to make sure. Well, I'm going to ask Wolfram Alpha to do this. Hmm?
What homework problems?
I'll have to look. I'll have to look.
I know what you're talking about because you did your videos, like the first section of one of the, or first section of a section, you did that.
So I'm going to integrate. Now I'm asking Wolfram Alpha to give me an integral on. Oh yeah. Okay, there it was. There it is.
You know what I realized?
Approximately.
E upside down L.
This, the gamma function.
What's the gamma?
Have you ever heard of one of the greatest open questions in mathematics? It is called the Riemann hypothesis.
We were saying something.
I've heard
Yeah.
Riemann stuff.
The Riemann hypothesis.
It was.
I think we talked about
It's
that.
an open question. I may have talked about that a little bit, but I talked about Riemann, but no, that was a different one that was solved. Anyway, okay, we're not going to get into the gamma function right now. But look, so when Mathematica does this, right, when this program is doing it and it gets this answer, does it have some magical way of doing it that we don't know? That's exactly what it's doing right there. Okay, it's using the power series to come up with the same thing we got. Pretty darn close, right? So, all right. What's what?
The big E.
The big E.
It says right there, it's the exponential integral. But then you're going to ask, what's that? Those functions are way out of the scope of this class. All right, so you just have to understand that those are like complicated like error functions, I guess you could say. They're basically saying like we can't get it in a nice closed form. If you want a nice closed answer, you're not going to get it. So for questions like this one, problems 47 through 50, page 488.
Which, bullet point is it? Sorry.
So the second to last one.
Second to last one. I do not believe that I did any homework videos over this. Maybe I did. I don't remember doing any. All right, everyone. Oh, that bonus lecture. I still haven't decided if I'm going to do one. Here's the problem is when we would do it. When's our final? Tuesday. I'm giving a final on Thursday. I'm giving a final at 12:30. Does anybody have a final on Thursday at 12:30 or at 1?
I do.
You do?
I'll have it from like 9 to past. From like 9 to. Or you said after 12:30?
Yeah.
Oh, then I think I'm good.
You think so?
I don't. 'Cause it's from
You
like
don't.
9
So everyone would be available at that time? You'd be available?
Well, they're all like 3.5 hours for.
Okay. It would be an optional thing that you didn't have to come to. I'm giving a final at 12:30, so what I could do is get them started on it and then just us go into a classroom next to it. Maybe. I don't know. The only other option is to do it at 11. We meet at 11 on Tuesday, Thursday, right? So any of you have a final at 11 on Thursday of next week? You do? Yeah. Would you be interested? I mean, you're not going to hurt my feelings, but would you want to come to?
Yeah.
You think so? Okay.
So what would it be over?
Fourier series?
Over the gamma function?
Fourier series? No.
And is it going to be like
Yeah.
an extra credit thing?
Normally it is, but see, here's the problem with that. If I offer it for extra credit, then everybody has to be able to come. And if we have any students that can't make it, it's not fair,
Yeah, that's true.
right? So, can I think about it? It's Thursday, right? Let me think about it over the next day. I'll send an email out and let y'all know. It might wait until Saturday.
Are you gonna give us a bonus question on
a bonus